Iniziare? Okay, let's start with the second lesson. So today we will speak about the entanglement, so the main quantum resource that we can, the most important quantum resource that we have in quantum information. So the basic concept before to introduce entanglement is try to introduce the fact that at the beginning, in quantum mechanics, we study the state as elements of a Hilbert space. Or to study the entanglement, we need to do a little bit a step further. So we have to introduce a structure in the Hilbert space. And we have to consider the concept of partitions. So the idea is that if we have an Hilbert space, we assume this Hilbert space can be written in general as a tensor product of different partitions that can be this way. And so forth. So we can decide to take as many partitions as we want. And from the physical point of view, one can think about the partition as some ways as a term is not needed, but so to have an idea, is like that there are part of the Hilbert space that can be assessed by one observer, but not from the others. So you can think about that you have an Hilbert space that describes, for example, 2 particles, 3 particles, whatever, in which one particle can be observed and measured, whatever you want, by one observable, and the second from the second one, a third one. So this means, for example, that if I am the experimentalist that is assessed the first particle, I can only look to this particle, the idea, but not to these other two. Imagine that there are only 3 partitions. Instead, you can access only B, she can access only C, or whatever. And so this means that we start to construct a partition inside the now we say
Sorry? We cannot hear you anymore.
Does it work now? No. Does it work?
Okay.
Oh, sorry. I don't know how it's happened. But okay, so suppose we can write the state in this way. So in this way,
The green light means it's on.
Yeah, in fact, there is no light. Okay, let's try.
The
During
battery
the-
is low.
Okay, it's possible to do something.
But it's like half an hour to charge it.
Yes.
Yeah. But we have another microphone, so maybe we can use this. And meanwhile, we can charge this.
When I
Yep.
do you have the charger? No, there's a USB. Okay, I think that we start. Do you hear me? On the
Sì, sì, si sente. Sorry, we hear you.
let's try to do faster because I know how much power battery we have in the for the mic, so let's go fast. So the idea is now is to try. So we prepared everything to start to discuss and prove the Schmidt theorem. So the idea is that if we have a system that is bipartite, it's not the right one. So we have something that can be written in this way. And if we have a pure state, it can always be written as a sum over I lambda I square. Then I will show you why this is no lambda I, sorry. I over A, I over B. There's two sets of state, which we can always write in this way. It is important because this will open up the path to arrive to quantify the time. So let's try to prove it this theorem. Let's start from the very beginning. So let's consider C as a general state defined on this system. So we will have a sum over n and m, Cn m, n over A, m over B. Then, okay, so this is a state. So the density matrix associated to this state is nothing else than m prime, Cn, m, E star, m prime, and a B m prime A, m prime B. So we have seen before that we can associate it, so we can obtain from this density matrix the reduced density matrix to the subsystem A, for example. And this is nothing else than rho A is n m prime and m Cn m C star m prime m and A and prime A. Okay, so this is a matrix. This is a Hermitian matrix. It's a positive matrix. Moreover, even if it's not important, it's a square matrix. So we can diagonalize this matrix. So so there will exist a set of state in which we can write this matrix as sum over I, something that is lambda I squared, I. So up to now, we've not do really nothing particular new. So we have an Hermitian matrix. We generalize this matrix. The point is that now let's consider what this implies. So suppose now we want to define state connected to this set of state I, but defined over the subsystem B. So the point is to define a system, let me call Li, that is nothing else than the system, so I. Now, as we see, so at the beginning, we write the state in two general bases. But we can always rewrite the state instead, so keeping still general on the B basis, on the B subsystem, but we can consider the subsystem I in this basis. So we can write down these, nothing else as I M C I M I over A M over B. And now we can write down this term here. So we have the state I is nothing so sum over I, sum over M, I, so suppose that is a fixed value of I bar, I bar times I M B, and then we have C I M. But this is our orthonormal, so orthogonal. So this means that these terms is different from 0 only when I bar coincide. So we can remove the sum, and we have, so this is nothing else than CEM B. Now, so this is now the point is, okay, this is a set of states that we have defined with these strange rules. The point is, the first question is, are these set of state orthogonal as they are the set of state I? We can try to test. So let's let's see. Okay, Li. Oh, so okay. The thing I want to write is Li Lj. This is from this expression. This expression. This is C. This is C. So sum over M prime over C I M C J star M M B sorry M prime J star M B M star A. But this is our orthonormal. What we obtain here, as you can see, that regardless of the coefficients, so what we obtain exactly the same coefficients that we have in the reduced density matrix of rho A. But while this is a generical basis, this is in the base in which the density matrix is orthonormal. So even so, if I and j are different, this coefficient is 0. So we are using the fact that in this way we reobtain again the reduced density matrix on A, but in a particular basis, the basis in which this density matrix, this reduced density matrix, is diagonal in form. So from this reason, for these things, we prove that Li and Lj are orthogonal, but are still not normalized. That's the point. Because if you write down if you write down if you write down Li, Lj, Li, so what you obtain from here is that this is the sum of E of CEM squared. But this is not a normalized condition. This is not normal because it's only the projection of one single state. So if this is called lambda square, from this we have that our state C can be written as sum over I A then over psi, but this is again at the state L, but has to be normalized, and then this is sum over I, L, I. And now calling this way, we prove it that there is this Schmidt decomposition. So for a pure state, only for a pure state, because we are using this, all this result is a fundamental, because otherwise all the step that I made here cannot be done. For pure state, if we can always write, so if we consider the partition, we can also write the state as in this form as a sum of I, the eigenvalue, so the square of the square root of the eigenvalues of the density matrix times the vector of the reduced the eigenvector of the reduced density matrix associated to the first for the respective eigenvalues, and times IB, the eigenvectors of the reduced density matrix of B. This is interesting because prove it that for the diagonal form, the two reduced density matrix are the same. This is interesting even because you can. So now we always made an example considering two qubits. So in this case, A and B are qubits, so both have the same dimension. But this is not a normal situation. You can have a situation in which one partition involves only one qubit, and the other one can be a huge amount of degree of freedom, or theoretically also a thermodynamical one. So you can, this especially when you consider a system, when you go to study the complex system, you usually look to entanglement of a small subsystem, not always, but often, a small subsystem, and how this small subsystem is entangled with a larger one. So, but this means that if the small subsystem have only a finite number, 3 or 4 or 5 or whatever it is, different state associated to an eigenvalue, so the reduced density matrix that is different from 0. This is true also for the larger one. So you know that you can have a density matrix. So your system can have an Avogadro number or degree of freedoms. But for this property, you know that when you go in the basis of the eigenvectors of the reduced density matrix, you can only have the num 3, 4, 5, whatever. So the number of the eigenvector that is different from 0 that is induced by the smaller part. The point is that in this way, you define a clear way in which you introduce a particular decomposition that is strictly connected with the entanglement property. In fact, suppose that there is only one coefficient that is equal to 1, all the other is equal to 0. This means that your state is separable. On the contrary, if you have, because you have a decomposition that is up with the tensor product to state. On the contrary, if your state is associated with, instead if you have 2 or more different coefficients, you have entanglement. Because in this way, you cannot write anymore the state as a tensor product, as a linear combination of tensor product, even if because the state is pure. So these allow you to create a distribution of probability that is strictly connected to entanglement. Yesterday we have seen that when we have a distribution of probability, we can associate an entropy measure that can quantify the amount of information that is connected to this distribution of probability. The classical version is the Shannon entropy. The quantum version is the von Neumann entropy. So the idea is that in this way you can measure the entanglement between a partition only when the initial state is pure, as the amount of information connected with the distribution of eigenvalues lambda I associated to the density matrix when we consider a partition, to the reduced density matrix. So the idea is that a measure for the entanglement can be written. So if we have a state psi that with a Smith decomposition can be written as sum of I, lambda I, AI, AB, then what you obtain is that you can associate as a measure of entanglement as of state C, the amount of minus over I, lambda I squared, log 2 lambda I squared. Obviously, lambda I must be positive because they are the composition of a physical state must be positive, and the values must be completed, included between 0 and 1. And this allows you to measure the entanglement for a pure state. So let me make an example. Again, our typical state, initial state, is always this. We can also change it, but okay. So we want to evaluate how much is the entanglement of this state. So obviously, in this case, we have 2 qubits. There is only one. So the only unique partition is to consider one partition made by 1 qubit on the left and 1 qubit on the right. So you can have the reduced density matrix, for example, for rho A, it is the trace over B of the state C. Then in this case, this state, so this density matrix can be written again as alpha squared, beta squared, 0, 0. In this case, there is no need to do Smith decomposition. This is already written in a way that resembles Smith decomposition. And then the entropy of this. So the amount of the entanglement that we have in system can be written as minus alpha square log over 2 square plus minus beta square log over 2 beta square. It seems that stay otherwise. The point that I want to so this choice is based on what we said before. So for pure state, we have the advantage when we made the Schmidt decomposition, the entropy that we evaluate on a subsystem is equal to the entropy that we evaluate on another subsystem. This is not anymore true when we consider a pure mixed state. So this is one of the reasons, because you cannot associate from a mathematical point of view, this is the reason, because you cannot associate the entropy of phenomena with the reduced density matrix to the measure of to the amount of the entanglement. In a way, from a physical system, you can consider that when you realize a partial trace, if there is entanglement, you are destroying the entanglement, and all this destruction of the entanglement is, in a way, it's something that comes out as an increment of information that can be detected by the phenomenon. The point is that when you start from a mixed state, you already have some information associated with the mixed state, because the probability is not 0 and 1, you have something different. But then, what you take, so you cannot discriminate between the two sources. So theoretically, the point that you have to do is that take your state, take all the possible decomposition in a mixed state in a density matrix that we said before, because we told that in a case of a mixed state, we can write an infinite number of even for maybe we have different decomposition. Theoretically, we have an infinite number of this decomposition. So theoretically, to understand what is the amount of entanglement, you need to go over all possible decomposition, find the entanglement. This is a pure state. The entanglement of each single pure state following these rules, making this making the average with the weight pi over all this quantity, and evaluate this quantity for the first decomposition, the second, the third one, and then minimize over all possible decomposition. The problem that it is, since it is an open problem, is extremely hard to be realized. There are situations in which can be evaluated quite easily. There are two. So one approach is with the concurrence, that I don't want to enter now. Eventually, we can discuss another time. But the point is that the concurrence works only when you have or two qubits or a qubit and a qubit, nothing else. So there is only these two cases, and moreover, qubit and qubit is also extremely hard to evaluate. But okay. Theoretically, with this approach, you can do both these two cases, one qubit, so two qubits or one qubit and one qubit. So a system with two levels, a system with only 3 levels, but nothing else. In all the other cases, there are particular situations in which you can find the decomposition, but there are particular states that there is not a general solution. Okay, let's see if so there are two things that can be interesting. Okay, let me do something fast. Yes, it works. Okay, let me do something very fast. So up to now, we have discussed the concept of entanglement when we consider a bipartition. So we have a system, we split in two, and we have the entanglement between these two systems. Now, I want to try to illustrate you not all the concept of multipartite entanglement, because it will be impossible to do in so probably will require a single course, so 4 lessons only for multipartite qubit, for multipartite entanglement. But I want only to give you some idea to understand where all the problems are connected to the multipartite entanglement runs. So consider these things. So what does it mean that a state is more entangled than another one? The point is so we show it LOCC operator that you can only reduce the entanglement. So you can, if you have a state with a certain amount of entanglement, you act with a LOCC operator, and then you can reduce this amount of entanglement. Now, suppose that you have two states, and then you can say, at this point, it's easy to say, no, what happens? So when I have an entanglement, so if I can go from state A to state B with a LOCC, this means that the entanglement of state A is greater than the entanglement of state B, because I can only reduce. If on the opposite, I can go from B to A, since B and A are B is greater than A. As if I can go in both the two directions, this means that the entanglement is exactly the same, and I have to choose a LOCC that preserves the amount of entanglement. But this means that I can really make this comparison, but there is an assumption in this way, that all entangled state can be bring from the state that is with higher entanglement to a state with a lower entanglement. In so way, all entangled state can be connected by LOCC, or in one direction or in another. But now, let me underline one point. Let me now generalize the situation when we have, instead to have bipartition, we have a tripartition. So in this case, at the first, we have to say that we have several different forms of entanglement, several different forms of state. So at the beginning, we have the states that are fully separable. So if we have a tripartition, we have a state that is A tensor B tensor C. This state is completely separable because it can be written with a tensor product with the state defined on A, state defined on B, state defined on C. And now, this is not the only case. So we have a system in which we have a particular situation in which your system can be written like rho A tensor, state, for example, rho BC, in which so there is entanglement between two partitions, now BC, but can be also the other. But this state is separable with respect to that. So in this case, we have entanglement, but there is not a genuine multipartite entanglement. For example, that is interesting because you can also create something more complicated. So imagine that you have a state rho that is, for example, P1, that is for rho A tensor rho B C plus P2 rho A B tensor rho C plus P3 rho AC tensor rho B. So in this case, one can say, okay, there is a multipartite entanglement because I cannot write each single term separately, because if I try to take a row A as a product, all these two states does not work well, because I have to break the entanglement here, I have to break the entanglement here. The same goes for row B, or the same goes for row C. No, this is not true, because again, it's true that there is an entanglement between all these terms, but all this entanglement that does not derive directly from for a truly multipartite entanglement. They're only a mixture between a state with an entanglement only between two partitions. Third step, the only state that we consider really as a multipartite entanglement, the state that cannot be written in this way, cannot be written in this way or this other. So a state in which you can never, even for a single decomposition, move away one of the state defined on a partition. Now, okay, without entering too much in the details, but was in 2003, yes, 2003, the work of Dur, Vidal, and Sirac, in some order, I don't remember, in which they proved that there are, in the case in which each one of these partitions is a qubit, so we have 3 qubits, we have two different states, two different family of entangled states. This is the point that I want to show you, that show how complicated is this problem. We have the GHZ state, family of state is 1, and the state that is called a W state that is called in this way. 100 plus 010 plus 001. So now, what do we say before? We say that when a state is entangled, when a state is more entangled than another,